Hello there, statistic lovers. This is Kimmo Soirinen, and this will be a introduction to statistics. Let's go. Statistical analysis are conducted on collected data. So you need data, you need numbers in order to conduct statistical analysis. And what data is, they are observations on variables. And variables, they are characteristics that can vary. So for instance, in the human population, we have income. It varies between individuals. So that's a variable in the human population. Degree of depression measured with some instrument. Some people have high values, others have lower values, so it varies, so it's a variable. Treatment group, that's also a variable. You conduct a study, you divide your participants in the treatment group and control group. So you have variation in this. In this case, a dichotomous variable. So observations on variables gives you data, and those you can conduct statistical analysis. So number of heads, for instance, in the human population is not a variable because everybody has one and only one head. So you would never find, for instance, a difference in mean number of heads between two groups, because the mean number of heads would be one in each sample. You wouldn't even be able to conduct t-test as it would be in this case, because you don't have any variation. You don't have any standard deviation in the group, so you could not calculate the t-value and so on. And you could not calculate a correlation between number of heads and something else. You need to have variation. It needs to be a variable. The variables you have data on, they can give you differing amounts of information. And depending on how much information they contain, it's quite usual that variables are divided into four different groups, different levels of measurement. So we have nominal scale variables, ordinal scale, interval, and ratio scale. And this is in order of increasing amount of information the variables give you. So if we have variables on a nominal level, nominal scale, then these are variables that people can have differing values on. Otherwise, it wouldn't be a variable at all. But it's not that much you can do with the information here. It's not much you can do with the values. So people have differing values, but you can, for instance, not rank the values. You can't speak about higher and lower values. People just have different values. For instance, sex or gender, we have females and males, but none of them is higher than the other one when it comes to sex or gender. It's just that they have different values. Treatment group, you have treatments A, B, and C. People receive different treatments, so it's a variable. It has variation in your sample, but none of them is more treatment than other one. So it's just differences. Differences in kind, differences in quality. Then you have a variable on a nominal level. And there are various things you cannot do with these kind of variables. You cannot, for instance, calculate an average on variables like this. It's you can't say the average treatment group was 2.4 or something like that. Another example, you have participants, they are born in different countries. They are born in Sweden, Finland, Norway, Germany, England, France, and so on. But you can't calculate an average on that information. You can't speak about average country of birth or something like that. So nominal scale. People have different values, but it doesn't give you that much more information. The next level here, ordinal scale. People can have different values, but you can also rank those values. But what you don't have is so-called equidistance on these kind of variables, on ordinal variables. And with equidistance, we mean that each step on the scale is equally large. So for instance, relative depression. If you have a group of individuals and you measure their degree of depression and then you rank them, 1, 2, 3, 4, 1 is the lowest degree of depression, 2 is the second lowest, and so on. Then you know that the higher your value on this variable, the more depressed you are. So person with value 3 is more depressed than person with value 2 and less depressed than the person with value 4. But what you can't know due to lack of equidistance is that if the difference between degree of depression between number 3 and number 2 is equally large as the difference between number 3 and number 4, you cannot know if the steps on the scale are equally large. So ordinal scale, what can you do with these kind of variables? Well, you can calculate, for instance, the median. Yeah, you can calculate the median on these kind of variables. You should actually not calculate the average, although it's quite common to do it. Okay, so if we have equidistance, then we're up to interval data, interval variables, interval scale. So people can have different values. You can rank order the values, and each step on the scale is assumed to be equally large. So you have equidistance. So for instance, degrees in Celsius, and quite often also Likert scale variables are assumed to be on interval level. So you ask people, how do you do? And they give you an answer on a scale from 1 to 7. From 1, I'm awful, to 7, I'm feeling like a little bird in sunshine or something like that. So then you would have a Likert scale, and those are quite often assumed to be on an interval level. So with interval data, you can calculate mean, you can calculate standard deviations, you can calculate all kinds of stuff on interval data. Okay. However, what you're lacking on interval data is non-arbitrary 0 point. So if you take the degrees in Celsius as an example, we have 0 degrees Celsius. It was pretty close to that this morning, for instance. But it's a non-arbitrary 0 point because 0 degrees Celsius doesn't mean lack of temperature. If it did, you couldn't have be below 0, but we quite often are below 0, for instance, here in Sweden. You couldn't have -5 degrees if 0 meant no temperature, lack of temperature. And because you don't have these non-arbitrary 0 points, what you can't do with interval variables is to calculate ratios. You can't, for instance, take plus, if it's plus 10 degrees one day and minus 5 degrees another day, you can't say that on the day with plus 10 degrees Celsius, it was twice as warm if you have 10 degrees Celsius and 5 degrees Celsius, you can't make a ratio and say that 10 degrees Celsius is twice as warm as 5 degrees Celsius, just because the number 10 is twice as much as the number 5. Because if that was the case, you could calculate ratios on this kind of variables, Celsius in degrees. What would the ratio be between 10 degrees Celsius and -5 degrees Celsius? Would you then say that 10 degrees Celsius -2 times warmer than -5 degrees Celsius? It wouldn't make any sense. So in order to be able to make rational ratios that mean something, then you have to have a non-arbitrary 0 point. And if you have that, then we're up to ratio scale here. The ratio scale, those are variables with the highest amount of information. So you can rank individuals, people can have different values, you can rank the values, you have equidistance, and you have a non-arbitrary 0 point. So for instance, height in centimeter, weight in kilos, age in years, and so on. So height in centimeters, you can have a person who is 2 meters long and another one who is 1 meter long, then you can rank them. The person who is 2 meters long is longer, is taller than the person who is 1 meter tall. And you can also say that the person who is 2 meters tall is twice as tall as the person who is 1 meter tall. So 2 meters is twice as much as 1 meter, but only half of 4 meters and so on. And because we have a non-arbitrary 0 point, 0 means lack of height in this case. So you can't have anything that is minus something centimeters tall or meters tall. So those are the scales. Depending on how much information we can get from the variable, they are on different levels of measurement. As a rule of thumb, we like information. We think information is good. So if you can choose, we always try to get data on as high level of measurement as possible. So for instance, if we want to know what age people are, maybe we want to do some kind of calculations with age involved. Maybe we want to correlate age with something else, life satisfaction or something else. Then we could collect data on people's age in different ways. For instance, here we have one question on the left. We ask people to tick the right box depending on their age. So 0 from 0 to 19, the first box, 20 to 39, the second box, and so on. And question on the right, we just ask people to write down their age on the line there. So if we see this question on the right, people put down their age on the line there, we get data on the ratio level. So if somebody puts 18, then we know that this person is twice as old as somebody who is 9 years old. And we know that the person who is 18 years old is only half the age of somebody who is 36 years old, and so on. So we have ratio data. We can do all kinds of stuff with this data. However, would we collect data on people's age with a question on the left here? So we ask them to tick the box. What level of data do we get then? Well, it's absolutely not ratio level. I guess we could say it's on an ordinal level. So we know if two people have ticked different box, then we know that one of them is older and the other one is younger. And we know which one of them is older and younger. But we don't really know the difference in age between those two persons. And well, and if two people ticks the same box, we don't know if they're the same age. They're probably not. Higher probability that they're not of the same age. So there's all kinds of the information lacking if we collect data about people's age with a question on the left here. So if I got to choose, I would collect data with a question on the right here. It gives you more information about people's actual age. Statistics could be divided into two main categories. We talk about descriptive statistics and inferential statistics. And descriptive statistics, as the name indicates, is used to usually describe how it looks like on certain variables in certain groups. Descriptive statistics could, in its turn, be divided into two main categories: measurements of central tendency and measurements of dispersion. And we'll talk about those in just a moment. And inferential statistics That's what the rest of the course after today will be about. It's with inferential statistics, you estimate probabilities. Usually, well, quite often the probability for a null hypothesis to be correct, or actually the probability of getting the data you have given that the null hypothesis would be correct. But for now, inferential statistics, you estimate probabilities, and those probabilities you use in order to draw conclusions. So measurements of central tendency is one type of descriptive statistics. What you do with this is that you give a summarizing description of a certain group on a certain variable. So you have a number of individuals in a sample, and you want to summarize, and each of them, they have a value on a variable. You want to summarize all of those values with one single value that in the best way summarizes how it looks like in this group of individuals on this variable. So that's the goal of measurements of central tendency, to give the best summarizing description. So we're going to have a look at 3 different measurements of central tendency, namely the mode, the median, and the most popular, the average. The mode is one measurement of central tendency, and it equals the most common value. So imagine, for instance, that we have 9 persons and we measure them. Each of those 9 individuals we measure on level of anxiety and level of depression. And we get the following values, as you see here. And then we can see that the mode for anxiety is 0, because that's the most common value. Of those 9 individual values, we have 1, 2, 3, 4, 5 zeros. We have 2 ones, 1, 2, and 1, 4. So the most common value, the mode on anxiety, is 0. And on depression, we have 2 values that are equally, and the most common, that's 5 and 8. We have two observations each of those 2 values. Of the other values, we have only single observations. So in this group of 9 individuals, the mode on depression is 5 and 8. So the mode is not very common. Measurement of central tendency. I don't think I personally have ever myself calculated the mode, but it's the only measurement of central tendency for nominal data. On nominal data where nominal variables, individuals can have different values, but you can't rank them. Then mode is the only measurement of central tendency that it makes sense to calculate. However, on those kind of variables, it's more common to calculate frequencies, like on country of birth. So if your respondents are born in 5 different countries, instead of saying which country of birth is the most common in your sample of individuals, you give frequencies, you give percentages. How many are born in Sweden, Finland, Denmark, Norway, and Kenya, respectively? So not a very common measurement of central tendency. Another much more popular measurement of central tendency is the median, the middlemost value. So for instance, here we have, what do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9 persons on level of anxiety. So what we do then, we sort the values from the lowest to the highest, or if you wish, from the highest to the lowest. And then the median is the middlemost value. So in this case, we have a 0 as the middlemost value. And so the median level of anxiety in this group of 9 individuals is 0. And similarly for depression, we sort them from the lowest to the highest values. Lowest to the highest value, and in this case we have 8 as the middlemost value. So the median depression in this group of individuals is 8. On the previous slide, we had 9 observed values, and then of course you only have one value in the middle. So with an uneven number of values, there is one value in the middle, and that will be your median. How about if you have an even number of values, then you have 2 values in the middle. So how do you calculate the median then? Well, in that case, the median will be the average, the mean of the 2 middlemost values. So for anxiety, we have sorted them from the lowest to the highest value, and we have a 0 and a 1 as the 2 middlemost values. So in this case, the median will be the average of those two. So the median level of anxiety in this group of individuals is 0.5. And the same for depression. We sort them from the lowest to the highest, and we have 7 and 8 in the middle as the middlemost values. So the median depression in this group is 7.5. So as I said, median, quite popular. And median as a measurement of central tendency, it goes hand in hand with variables that are on ordinal level. Because if you have ordinal level data, then you can rank them. So you know what if a value is lower or higher as another value, but you don't know how much higher it is. So for instance, here for depression, we have a value of 218, which is as a value much higher than the other ones. But if depression, the scale we use for depression in this case would be considered to be on an ordinal level, then we know that 218 is higher than the other values, but we wouldn't say that 218 is much higher than the other values. It's just the highest value. And so we get the median of 7.5 here. If this person with 218 in depression would have 21 instead, the median would still be 7.5. And that kind of makes logic, because we would say that 21 is the highest value, it's higher than 19, and we say that 218 is highest value, it's higher than 19. But in neither case would we be sure about how much higher the highest value is compared with the second highest value. So median and ordinal data go hand in hand. The mean is the most popular measurement of central tendency, and it equals the sum of all observed values divided by the number of values. So this is actually the arithmetic mean, because there are other means. There is something called the harmonic mean and something else called the geometric mean. Well, those are the ones I know of, might be even more. So I guess all of you have calculated the mean on some occasion. So we have some formulas here. If we look on the left here, in formulas it's quite commonly, but there are other notations used also. But using this Greek letter μ, it's called. So the formula on the left says here μ, the population mean, equals sigma, that's the E-looking letter, that's the Greek sigma x, that means the sum of x. X stands for observed values, so it says and n is equals number of observations. So it says me, the population mean, equals the sum of all observed observations x divided by number of observations n. And on the right we have the same formula, but it's quite common if you have a formula for calculations of mean in a sample, then you don't use me. Instead, you use this x with a line above it, x bar. But of course, the formula says the same thing. The mean equals the sum of all observed values divided by number of values. As an example, here we have 9 individuals and we have a measure of their level of depression. So we calculate the mean in this group of 9 individuals. So we take the sum of all the values, 5 plus 5 plus 6 and so on, divided by number of observations, 9. So the mean level of depression in this group of 9 individuals is 31.78. And the mean is the measurement of central tendency that takes into consideration the most information. And that's, I guess, we usually think that's a good thing. We don't want to ignore any information. All information is welcome. All information we want to take into account. However, this at the same time makes it more sensitive for outliers compared with, for instance, the median. So in this example, we see that 31.78. So could we consider that to be a nice, a good summarizing descriptive value for how it looks like on depression in this group of 9 individuals? Well, maybe not. It's this mean 32 is higher than 8 of the 9 values. And it's almost, well, not well. It's pretty much higher than the second highest value of 19. And the reason for this is, of course, that we have this extreme outlier, a person with 218 in measured depression. So the mean is sensitive for outliers, as in this example. Had we calculated the median instead, so the median would be 8, and had the extreme outlier been 21 instead of 218, the median would still be 8. And had the highest value, instead of being 218, been 2,180, the median would still be 8. So this indicates that the median is not sensitive for outliers. It's the middlemost value. How high or low the most extreme values are doesn't infect the median to any high degree. While in all of those examples, the change of the extreme value will result in a change in the mean. But still, we're going to use the mean in our examples, in our calculations further on in this lecture. So measurements of central tendency. You summarize a number of values with one single value that supposedly gives you the best description of how it looks like in this group of individuals on the variable in question. But of course, the measurement of central tendency, the mean or the median or whatever you're using, seldomly gives the full picture of how it looks like in the group of individuals on the variable in question. As an example, imagine we have 2 groups, group 1 and group 2, with 8 individuals in each group, and we have the mean 10 in each group. So if that was the only thing we knew, that the mean is 10 in both groups, we might believe that it looks the same in these 2 groups when it comes to this variable, depression or whatever it is. But we see that's not the full truth, the whole truth. In group 2, the individuals vary between 8 and 10, so they are very tightly grouped around the mean of 10. While in group 1, we have variation from 0 to 20, so you have much more dispersion in group 1 in group 2. But that we would not know if we only knew that the mean is 10 in both groups. So in order to give a fuller picture of how it looks like in a certain group of individuals on a certain variable, we quite often calculate measurement of dispersion besides measurement of central tendency. And we're going to have a look at two of them, range and standard deviation. Range is one measurement of dispersion, and it equals the difference between the highest and the lowest value. So it's quite crude measurement of dispersion. So in our example here, the range in group 1 is the difference between the highest value 20 and the lowest value 0. So the range is 20 points, the difference between the highest and the lowest value. While in group 2, the range is the difference between the highest value 12 and the lowest value 8. So the range in group 2 on this variable is 4 points. And of course, as the range is based on the most extreme values, the highest and lowest value, it's extremely sensitive for outliers. So if the highest value in group 1 would have been 200 instead, then the range would be 200. So it's very sensitive for outliers. Another much more popular measurement of dispersion is the standard deviation, and it equals more or less, it's not exactly true, but more or less the standard deviation gives us how much observed values on average deviate from the mean. So if we have the two groups, group 1 on the left and group 2 on the right, and in both of the groups we have a mean of 10. So if we would calculate, and each dot is observed value. So if we would calculate how much those dots deviates from the 10, from the group mean, and so for instance, the leftmost value in group 1, it's 0, so it deviates 10 from the mean 10. And the highest value 20 also deviates 10 from 10. So it's the deviation from the mean, and we don't consider if it's on the negative or the positive side. In absolute values, the absolute deviation from the mean. So we see in these figures, it illustrates that the average distance, the average deviation from the mean, it's much larger in group 1 than in group 2. So in this case, we would get a larger standard deviation in group 1 compared with group 2. More deviation from the mean, more dispersion in group 1 compared with group 2, and therefore also a larger standard deviation. So here are the formulas for the standard deviation. And they pretty much give what I described in words. How much observed values on average deviate from the mean. The average distance between the values and the mean. So if you have a look on the formula to the left, so quite commonly, that's the small sigma, stands for the standard deviation in the population. So the standard deviation is, and we see in the ratio here, in the denominator, we have the sum of deviations between observed values x and the population mean mu, and we square that because otherwise the positive and the negative differences will take each other out, and we always get the standard deviation of 0. So we square that difference and we divide by number of observed values n, and then because this would give the average, the mean square difference from the mean. So in the end, we take the square root of this. And what we have left could, in words, be described as how much the observed values on average deviate from the mean. It's not completely true verbal description of what we get from the standard deviation, but it's quite close to it. And the formula on the right, the same for samples. The standard deviation equals the sum of observed differences between values x and the sample mean x bar. We square those differences and we divide by number of observed values, but in this case number of observed values minus 1, because otherwise this formula would actually tend to give a smaller value than it should. And then we take the square root of this. Okay. The standard deviation is this in the same unit as the variable it is calculated on. So if we, for instance, in a group of individuals have an average height of 180 centimeters with a standard deviation of 10, then that standard deviation would be 10 centimeters. So if we calculate height in centimeters, then we get the standard deviation that is in centimeters. So in this case, the value 10 would tell us that on average, the individuals in the samples have a height that deviates 10 centimeters from the group mean of 180 centimeters. Had we had the same data, exactly the same data, but height in meters instead, then of course the average height in this group of individuals instead of 180 centimeters would be 1.8 meters. And in that case, we would get a standard deviation. Can you guess what it would be? Well, it would be not 10 centimeters, it would be 0.1 meters. So in that case, it would tell us that on average, the observed heights of these individuals deviate 0.1 meter from the group mean of 1.8 meters. And of course, that's the same thing. Okay, so the standard deviation will follow the scale we are using, and it will be in same unit as the variable we are doing the calculations on. Variance is another measurement of dispersion, and it equals the square of the standard deviation. So if you compare the formulas here with the formulas for standard deviation, you see the only difference is that they lack the square root that we have in the formulas of the standard deviation. So we could say, while the standard deviation gives how much observed values on average deviate from the mean, the variance gives how large the squared deviations from the mean are on average. Variance is usually not used so much in itself as to describe how it looks like in a certain group of individuals on a certain variable, but it's included in various statistical analysis. For instance, analysis of variance. What you do with that method is that you calculate variances. In simple form, you calculate the variance between groups and variance within groups, and from the ratio of those you draw conclusions. But more about that later when we have analysis of variance. Now, I guess for now it would be enough for you to identify that there is a measurement that it's called variance. Now we come to a new subject, this set of values, standardized set of values. So while measurement of central tendency, for instance, the mean, and measurements of dispersion, for instance, the standard deviation, those are parameters on the group level. So you have one mean and one standard deviation on a certain variable in a group of individuals. The individuals don't have a mean or a standard deviation. However, the zeta value that you can calculate for each individual, and the zeta value that gives it equals the relative deviation of this person's observed value from the mean. So how much a certain individual value deviates from the mean in relation to the average deviation from the mean. And as you know by now, the average deviation from the mean, it's called the standard deviation. So you have the formula here. So if you have observed value x, if you want to transform it to a standardized zeta value, you take the observed value x minus the mean, x bar, and you divide by the standard deviation. So the zeta value will give you how many standard deviations the observed value x deviates from the mean. So if you take a value x and you transform it to zeta value with this formula, and you get a value of +1, then you know that this value x is one standard deviation above the mean. And if you get the value -2, then you know that this observed value x is 2 standard deviations below the mean. So all values above the mean receives a positive zeta value, and all observed values below the mean would receive a zeta value that is negative. And value that is identical with the mean would receive a zeta value of 0. And of course, standard deviations is how large the average deviation is from the mean. So if you take a value x and transform it to zeta value, and you get a value that is either +1 or -1, then you know that this value x deviates as much from the mean as the observed values do on average. While if the zeta value equals -2 or +2, then you know that this value x deviates twice as much from the mean as the observed values do on average. Another thing we could say about the zeta value is that it is a measure of extremeness, how extreme a certain value is. So if you take a value x and you transform it to a zeta value, then you know that the more this zeta value deviates from 0, the more extreme the value x is. And the more extreme the value is, the lower is the probability to receive another value that deviates even more from the mean that this value x does. So if you take a value x, you transform it to a zeta value, then you know the more this zeta value deviates from 0, the lower is the probability of receiving another value that deviates even more from 0, that is even more extreme than this first value x. So the zeta value could be said to be a measure of extremeness, how extreme a certain value is. As an example, imagine that we have a population mean on the variable depression among Swedish women, a population mean of 10, and a population standard deviation of 3. While among Italian men on the variable IQ, we have a population mean of 100 and a population standard deviation of 15. And now we ask ourselves which probability is higher and or lower that the Swedish woman randomly selected from the population is more depressed than 12, or that the randomly selected Italian man has an IQ less than 80. Which of these two outcomes is more probable? Well, in order to do the comparison here, because it's two different populations, two different variables, we have to standardize those values first. So we transform them to a zeta value. So if we take the value 12 on the variable depression among Swedish women, we would calculate 12 minus 10. That's how much it deviates from the population mean. And we divide by 3, the standard deviation, and we get the value of 0.67. So in order to get a Swedish woman that is more depressed than 12, she has to be more than 0.67 standard deviations above the population mean. She has to deviate more than 0.67 standard deviations from the population mean. While for an Italian man to be have an IQ that is less than 80, how many standard deviations has his value have to deviate from the population mean? Well, we calculate how many standard deviations does the value 80 deviate from the population mean. We take 80 minus 100 divided by 15, and we get the value of minus 1.3. So in order for an Italian man to have an IQ less than 80, he has to have a value on IQ that is more than 1.3 standard deviations below the population mean. So now we see that the value 12 deviates only 0.67 standard deviations from the population mean, while the value 80 deviates 1.3 standard deviations from the population mean. This means that the value 80 on IQ among Italian men is a more extreme outcome than the value 12 on depression among Swedish women. And because 80 among Italian men on IQ is more extreme, the probability is lower to get an even more extreme value. So that outcome is less probable. While the probability of getting a Swedish woman that has a value on depression that is about 12, that is less extreme outcome. So that outcome is more probable. So by transforming values to zeta values, you can compare them, you can calculate, you can compare them and say which of these two outcomes is more or less extreme. And from that, the outcome that is more extreme, that outcome is less probable, while the outcome that is less extreme, that is more probable. Another characteristic of zeta transformed variables is that if you take a variable of values and you zeta transform all of the values, you will get a new variable, a new zeta transformed variable that always has a mean of 0 and a standard deviation of 1. As an example, in the table to the left, we have measured the degree of depression for 9 Swedish women, and we get a range from 6 to 14 with a sample mean of 10 and a sample standard deviation of 2.7. So imagine now that we transform each of these values to a zeta score. So for instance, for the first person here with a depression of 6, we take 6 minus 10 and divide by the standard deviation 2.7, and we get a zeta score of minus 1.46. This means that the value 6 is 1.46 standard deviations below the sample mean of 10. And another example, person 7 has observed depression of 12. If you take 12 minus 10 and divide by 2.7, we get the value of 0.73, it means that this observed value of 12 is 0.73 standard deviations above the sample mean of 10. So all of those women with the observed depression below the mean of 10 get the negative zeta score, and those with the observed value above 10, they get the positive zeta score. And person number 5 here with the observed value 10, that is exactly the same as the sample mean, receives a zeta score of 0. So now if we have a look at this variable of zeta transformed variables values, and we calculate the mean and the standard deviation of this, we see we get a mean of 0 and a standard deviation of 1. In the table to the right, we have 9 Italian men, and we have measured their IQ. We get a range from 77 to 123. So we have a sample mean of 100 and a sample standard deviation of 17.7. If we now transform each of these observed IQ values to a zeta score, we get a range from minus 1.3, meaning 1.3 standard deviations below the sample mean of 100, up till plus 1.3, meaning 1.3 standard deviations above the sample mean of 100. So now we receive a new variable of zeta transformed IQ scores. And if we calculate the mean of this, we get a value 0. And the standard deviation on this variable of zeta standardized IQ scores is 1. And it will always be like this. Take a variable, calculate the mean and the standard deviation, use those values in order to zeta standardize each of the values, and you receive a new variable of zeta standardized scores. And this variable of zeta standardized scores will always have a mean of 0 and a standard deviation of 1. Now we come to a new subject, correlations. Correlations are measures of the direction and strength of linear associations between two continuous variables. So if you have two continuous variables, and with continuous we mean that we can speak about higher and lower values. So it's no use calculating correlations between nominal variables, for instance. Because, for instance, a nominal variable country of birth, you can't speak about higher and lower values. You can't rank the values. So on those kinds of variables, you cannot calculate correlations. You can calculate associations with other means, but not with correlations. So you have two continuous variables. You can speak about higher and lower values. You can calculate the correlation between these two. And the correlation you get will be a value between -1 and +1. So it will be either negative or positive, or maybe 0. So if we take an example, so here we have a table with 5 persons with degree of introversion and degree of depression. So first person has a value of 19 on introversion and 18 on depression. So let's make a scatter plot. So we have a scatter plot like this, and we put in the first person with a value of 19 and 18, and we see it here. And then we take the next person with only 1 in introversion and 2 in depression, and here is a dot for that person, and we do like that for the rest of the persons. And let's imagine we have more than 5 persons, so we get a scatter plot like this, with introversion on the x-axis and depression on the y-axis. So what we have here is what we call a positive association. With positive, we mean that the higher your value on one of the variables, the higher value you tend to have on the other variable. So in this case, the higher you have on introversion, the higher you have on depression. The lower you have on introversion, the lower you have on depression. That's called a positive association. If you plot two continuous variables and you get a plot like this, a scatter plot, we see that the higher value you have on one of the variables, the higher value you have on the x variable, the lower value you tend to have on the y variable. And the lower on x, the higher on y. Not surprisingly, this is called a negative association. And if we, maybe as an example, if we have age here on the x-axis, so age might have a negative association, for instance, with physical activity. Maybe not a good example, because many people, they get a middle-age crisis when they're approximately 40 years old and start running marathons and so on. So maybe it's not completely true to say that physical activity tends to decrease linearly with age. Another example might be if we, on the y-axis, instead of physical activity, had something like eyesight, sharpness of eyesight. So if we had sharpness of eyesight on the y-axis, the scatter plot would indicate that the older you are, the less sharp eyesight you have. The younger you are, the sharper your eyesight. So that would be an example of a negative association. And of course, if you calculate the correlation for this with a negative association, you would get a negative correlation, a correlation below 0. I would guess if it looks like this, you would get a correlation of approximately minus 0.5, 0.6, something like that. And zero correlation, no linear association between two continuous variables, then the scatter plot might look something like this. So here you see if we increase the value on the x variable, there is no systematic change on the value on the y variable. So we see that the average value on the y variable is approximately the same independently of the value on the x variable. So if it looks like this, then we would have a correlation close to 0. No linear association between the two variables. So that's about the direction of the association, the correlation. We can either have a positive association, which gives a positive correlation. Negative association gives a negative correlation. And no linear association gives a correlation close to 0. How about the strength of the correlation? As said, the correlation can vary between -1 and +1. It cannot be outside this range. So if we make a scatter plot and it looks like this, so the observed points are in a perfect straight line. This means in this case we would get a correlation, a perfect positive correlation of +1. Correlations could be seen as measures of information overlap. So if it looks like this with a perfect positive correlation, it means that there is a perfect information overlap. So if we know that the person has, for instance, this value on the x variable, then we know that he or she must have this value on the y variable. There is no room for any diversion here. We know exactly what value a person will have on the y variable based on if we know this person's value on the x variable. So imagine it looks like this instead. So this could be a correlation of plus 0.9, something like that. Then we have high degree of information lap, but it's not perfect. So if we know that the person has this value on the X variable, then we can make a good prediction with a high precision about this person's value on the Y variable. But we cannot make a 100% perfect prediction about what value this person has on the Y variable. So correlation, measure of information lab, measure of how well we can predict the value on one of the variables based on values on the other variable. So if it looks like this, correlation of maybe plus 0.9. If we get more scatter, if it looks like this, might be a correlation of plus 0.7, something like that, and even more scatter. So here we have a weak positive correlation of maybe 0.2, and complete scatter, no linear association. The correlation would be close to 0. If we have a correlation of 0, then if we know a person's value on one of the variables, we have no use of this information if we try to predict the value on the other variable. So if we know that a person has a high value on the X variable or a low value on the X variable, it doesn't matter. It doesn't help us if we're trying to predict what value this person might have on the Y variable. There is no information overlap. Okay. In the other direction, if we make a scatter and it looks like this, then I think you have guessed, then we have a perfect negative correlation of -1. And one example of this would be, for instance, if you on the x-axis here have year of birth, then on the y variable you would have age. At the given point in time, the later you are born, the younger you are. The earlier you were born, the older you are. So a perfect negative correlation between year of birth, time of birth, and age. If you have some scatter, so here we might have a correlation of -0.9, and we add some more scatter, less information lap, less precision in prediction. So here we might have a correlation of -0.7, even more scatter, a weak negative correlation of maybe -0.2, and complete scatter, no linear association. We have a correlation of 0. One thing that is good to bear in mind is that the correlation, even a strong one between two variables, doesn't prove that the association is causal. So if there's a strong correlation between x and y, it doesn't say that x has a causal effect on y, or that y has a causal effect on x. As an example, imagine that we measure the whole population. I was going to say a whole Swedish population, but it can be any population. So we measure a whole population on two variables. We measure them on IQ. They fill in the best, most valid IQ test in the world, so they get the IQ score. And we also measure how long trousers they are wearing in centimeters. So a ratio scale. I'm quite sure, nobody has done this, but I'm quite sure we will find a quite strong positive correlation between trouser length and IQ. If this was a causal effect, what would it mean? It would mean that if trouser length has a causal effect on IQ, it means that if you manipulate the person's trouser length, you will also observe a change in their IQ. So for the same person, if they change to shorter trousers, we will see a decrease in their IQ. So if they're wearing shorts, the same person wearing shorts would have a lower IQ compared with the same person wearing longer trousers. And if they're wearing trousers that are too long for them, might make it difficult to walk, but the upside of this would be that they would have even higher IQ. That's what it means with a causal effect. If X has a causal effect on Y, it means that if you manipulate X, if you actively change the value on X, this will result in a change on the variable Y. However, I guess nobody thinks it's like this. Nobody probably thinks there's a causal effect of trouser length on IQ. So how come that we still, if we measure the whole population, would observe a positive association between trouser length and IQ? Well, that's because we have a confounder, a confounding variable. Confounding variable is a variable that has an effect, or at least an association, with the two measured variables, and due to this influence of this third causal variable, we will observe an association or correlation between these two other variables. And in this case, we could imagine, it's quite clearly that it would be like this, that trouser length and both trouser length and IQ is affected by the confounding variable age. So small children, they are wearing short trousers for the obvious reason that they have short legs. And at the same time, age has an influence on IQ. At least if you measure people's IQ with an IQ test that it's adapted to adult respondents. So small children have short trousers, and at the same time they receive lousy results on IQ tests, especially if they have not learned to read yet. Then they will get really bad results. And due to this influence of age on both trouser length and on IQ, we will observe a positive correlation between trouser length and IQ without them having any causal effect on each other. So that's the thing. A correlation between two variables could be caused by a confounding variable that influences both of them. Also, another thing about correlations, even if it is a causal effect, we cannot always be sure if it's a causal effect of X on Y or in the opposite direction of Y on X. For instance, this association has been observed. I don't think it has rendered any enormous attention among researchers, but I read a short article about this in a newspaper. There were some people who have observed a positive correlation, a positive association between how much people working hours, and their health. So we see a positive association between these. And the persons in this case, they argue that this indicates that the less people work, the worse health they will get. So they thought it was a causal effect of working hours on health. And they took this as an argument that we cannot reduce how much people work in our society, because if we do that, we will see a decrease in the level of health in our society. So they thought it was a positive causal effect of working hours on health. However, as you have learned by now, correlation doesn't prove causality, and in this case, it might be also that even if the effect association is causal, it doesn't have to be an effect of working hours on health. It could be in the opposite direction. It could be instead that the worse health people have, the less they work. The better health they have, the more they work. So it could be an effect of health on working hours rather than the other way around. So this doesn't prove that there is a causal effect at all, and it doesn't prove in what direction the causal effect would go if it actually is one. There are different correlation coefficients, but the most widely used is probably this one, the Pearson product moment correlation coefficient, usually called Pearson's correlation. You have the formula there. I won't go into it, but it gives you a correlation between -1 and +1, indicating the direction and the strength of a linear association between two variables x and y. This Pearson correlation is useful. You can use it, you can calculate it, but both variables, both x and y, should be at least interval scale. So either interval or ratio scale. If they are ordinal scale, there is alternative, so-called non-parametric correlation coefficient, an alternative that's called the Spearman's correlation. Spearman's rank order correlation, if I remember right. So that's an alternative that can be used if one or both of the variables are on an ordinal scale. If one or both of the variables are on the nominal scale, then you cannot calculate correlations. Because when you calculate correlations and you receive a value, then of course a positive correlation indicates that the higher your value on x, the higher the value on y, and vice versa. So you have to be able to talk about higher and lower values for a correlation coefficient to make any sense, to be interpretable. However, on variables on a nominal scale, you cannot talk about higher or lower values. For instance, country of birth. So if you have country of birth and calculate the correlation and receives plus 0.7, what does it tell you? It tells you the higher your country of birth is, the higher your value on the other variable. But it doesn't make any sense because you can't speak about higher or lower country of birth. If you calculate correlations and make statements about the linear association between variables based on this calculated correlation, it's always a good idea to actually plot the data to have a look, because it's possible to receive correlations that are due to strange things in your data. Not so in this case. So here we have plotted heights on the x-axis and weight on the y-axis. So we see a quite clear, strong positive correlation here. So this is actual data. We see here the taller people are, the more they weigh. The shorter they are, the less they weigh. So this is, and the Pearson correlation for these two variables are plus 0.7. If there's something strange in this, well, it's not strange, but we see here there's more scatter at the high end of the scale. So among those who are short, approximately 160 centimeters tall here, all of those weigh quite little. While among those who are tall, for instance, 190 centimeters tall, then there is more scatter in the weight among those. Okay. However, correlations, strong correlations, or correlations in general, could be due to stranger things. So here we see something that's called the Anscombe's quartet. So we have 4 panels here, and in each of these cases, in each panel, the correlation between the two variables is 0.816. So if we only hear about the correlation between two variables of a strength 0.816, of course we might imagine, and if it's our own data, we might hope that what it indicates that we have an association that looks like in the uppermost left panel here, because in that case there is nothing strange with this. We have some scatter, we have a clear positive linear association, but it's not the perfect one. There's some scatter. However, the same correlation, 0.816, we have in the upper right-hand panel, But clearly here, instead of having a strong positive linear association, we have a perfect curvilinear association. So in this case, we should analyze and interpret the association not with a correlation, but for instance, with a curvilinear regression analysis instead. In that case, we would receive the result that the value on x to 100% can explain the value on the y variable. But it's not a linear association, it's a quadratic association instead. In the lower left panel, we see that we have a perfect positive correlation of +1, except for one individual that has a higher value than expected. And this person destroys the perfect positive correlation, decreases it from what it otherwise would be, +1, down to 0.816. So here we see what might be actually a perfect positive correlation, but due to something strange, we have one individual that destroys this. And in the last panel, the lower right-hand panel, we see that here we have no association between the two variables because everybody has the same value 8 on the x variable. So there's no variation in x. And if there's no variation in x or in y, then automatically the correlation would be 0 because you need variation on both x and y in order for there to be a correlation between these two. So here there would be no correlation between x and y. However, we have one outlier, one person who has a much higher value on x and a higher value on y than the other ones. And only due to this single individual, instead of having a correlation of 0, we have a strong positive correlation of 0.816. But of course, if you have data like this, it would not feel right to draw the conclusion there's a strong positive association between x and y. Because if that's the only thing you hear, you might draw the conclusion, okay, the higher value people have on x, the higher value they will have on y. But here, clearly, the full association is only due to one person. So we would need to be very careful about drawing a conclusion about the association between x and y if we have data that look like this. So what we learn from this, what we learn from Anscombe's quartet, is that before we make strong statements about association between two variables based on a calculated correlation, we should always have a look at them, what they look like, by plotting them in a scatter plot. Next subject here, distributions, frequency distributions. As a simple, quick example, imagine that we measure a lot of individuals on level of depression. So in this case, we get scores with a range from 2 to 18. And then we have a look, how many individuals have the score 2? And we say that it's relatively few individuals with such a low score. How many have a score of 4? Approximately 100 individuals. And 250 individuals have a score of 6, and so on. And we have a peak at the mean here at 10, approximately 500 individuals with a measured depression level 10, and then it decreases again. So there are a few individuals with a low score of 2, there are a few individuals with a low score of 18, and there are a lot of individuals around the middle here with a peak at the mean. And if we, instead of having bars like this in the panel to the left, we draw a line, then we get the figure on the right here. It's the same frequency distribution, but with a line instead. And now this frequency distribution with this bell-shaped curve, bell shape, it's called a normal distribution. Although it's called the normal distribution in singular, it can look differently. So sometimes the normal distribution can be more peaked, and sometimes it's more wide. And what decides the wideness, the peakness of the normal distribution, it's the degree of dispersion we have on the variable in question here. So the more dispersed the variable is, the wider is the distribution, and the less dispersion we have, the more peaked is the distribution. And dispersion, our favorite measure of dispersion is standard deviation. So that means that with a small standard deviation, we get a more peaked distribution. And with a larger standard deviation, we get a wider distribution, even if they might be normally distributed, both of them. Not all variables are normally distributed. Some variables have skew. Some variables can have a lot of skew. So we talk about positive and negative skew. Positive skew, then you have skew to the right towards high values. And one example of this in most populations is, for instance, income or salary. So let's imagine we have a frequency distribution that looks something like this. It means in this case that the difference, we have a peak at 25 and the lowest value is 15. So that's a difference of 10. If we go upwards the same amount, we come to 35. But there are people with much higher salary, much higher income than 35. So in a positively skewed variable, the difference between the most common value, the mode, the peak of the curve, and the lowest value, that the difference is smaller than the difference between the peak and the highest value. Then we have a positively skewed variable like this. On a positively skewed variable, the mean is higher than the median. The median is lower than the mean. Negative skew, then we have distribution, something like in the panel to the right here. Then it's of course the opposite. The difference between the peak and the highest value is smaller than the difference between the peak and the lowest value. We have a skew towards low values to the left. Age at death could be like, I think age at death has a negative skew in many populations. So maybe the oldest people, they die at age 120, and maybe we have a mean life expectancy of 80, something like that. So that would be a difference of 40 years. If we go in the other direction from the mean of 80, we land at 40. And although not many people die before the age of 40, of course there are some. You can die as soon as you've been born. So that means we have a skew to the left like this. And on a negatively skewed variable, the mean is lower than the median. The median is closer to the peak of the distribution, while the skew, the low values, drag the mean towards them. So we get the mean that is lower than the median. The median is higher than the mean. Let's talk some more about distributions, but of sampling distribution instead. So what we had to look at just now was the distribution of individual values, but we could also have a look at and talk about the distribution of sample means. And we do this through a little simulation. So imagine we have a population of 1,000 individuals on a variable. let's say it's depression. So we have a range here from slightly less than 2 up to 9 something. So these 1,000 individuals have a mean of 5.52 and a standard deviation of 1.25. So let's imagine we do the following. We take these 1,000 individuals and we pair them. We divide them into pairs, so 2 people in each pair, and we do this completely randomly. And then for each pair, each of the 500 pairs, we calculate the mean on this variable depression. So instead of 1,000 individual values, we have 500 sample means, sample size 2. And then we have a look at the frequency distribution of these 500 pair means. And what will we see then? Well, we see the following. The mean of these 500 pair means is the same as the mean of the 1,000 individual values. It doesn't change because it's exactly the same observed values in the bottom here. So we have a mean of these 500 pair means is still 5.52, the same as the mean of the 1,000 individual values. However, we see a decrease in the standard deviation. So the standard deviation of these 500 pair means, instead of 1.25, it's 0.87. How come? How is it only random? No, it's not. So how come it becomes smaller? Well, imagine the following. So we take an individual with a very high value. So let's say we take one of these 1,000 individuals. We take a person with a value of 9 on depression here. And as you see, it's in the right-hand tail of the distribution here. And then we pair this person with one other person from the same distribution, randomly selected. We can be quite sure that this other person will have a value that is lower than this person's value of 9. There is some probability of this person having a even higher value than 9, but that probability is very low. Why? Well, because almost everybody has a value that is lower than 9. So with very high probability, this person with a high value of 9 will be included in a pair with somebody who has a lower value than him or herself. And because this other person has a lower value, the mean of their 2 values will be lower than 9. So people with extremely high values will tend to be paired together with others who have lower value than themselves, and therefore the pair means will tend to be lower than the individually high values. So the tail in the right-hand side here, it shrinks in towards the middle. And we have the same phenomena for people with extremely low values. People with a low value of 2 will tend to be coupled with somebody who has a higher value than themselves. Because the other person has a higher value, the pair mean will be higher than a value of 2. So people with extremely low values will tend to couple up with others who have a higher value than themselves, and therefore the pair mean will be a higher value, and the tail on the left-hand side of the distribution shrinks in towards the middle, toward the middle. So both tails shrinks towards the middle, and we get a peakier distribution with a smaller standard deviation compared with the 1,000 individual values. And if we continue, instead of making pairs, we divide the 1,000 individuals randomly into small samples of size 5, so 5 persons in each sample, and we do the same thing again. We calculate the sample mean for these 200 samples with 5 persons each. We calculate the mean of those 200 sample means and the standard deviation of those 200 sample means. And what do we see here? Well, the mean of those sample means is still the same as for the individual values, 5.52, but we get even larger shrinkage towards the mean. So we get the even peakier distribution with an even smaller standard deviation. In this case, the standard deviation of these 200 sample means is 0.6. And if we continue even further, we divide the 1,000 individuals randomly into 50 samples with 20 persons each. The mean of the 50 sample means is still 5.52, but we get an even smaller standard deviation. The standard deviation of these sample means is 0.26. We get an even peakier distribution. And if we eventually, lastly, divide 1,000 individuals into 10 samples each, randomly with 100 people in each sample, we have a mean of the sample means is still 5.52, but we have a very peaky distribution with a standard deviation of 0.12. And of course, the standard deviation of 0.12 is much smaller than the standard deviation of the 1,000 individual values of 1.25. So what we learn from this is that if you take samples from a population, the sample mean gives you an estimation of the population mean. Sample means don't tend to be higher or smaller than the population mean. However, sample means very often, almost always, is not exactly the same as the population mean. However, the larger samples you take from your population, the less will the sample mean tend to deviate from the population mean. So if you are going to use a sample mean as an estimation of a population mean, you get a better estimation the larger sample you have. So here I have plotted sample size on the x-axis, not in scale, you see that, but those are the sample sizes I used in the simulation. We have a standard deviation on the y-axis here, and so we see that the standard deviation decreases from 1.25 for the individual values down to 0.12 when we have samples of size 100. So this is the observed association in our little simulation. However, there's a theoretical mathematical formula that gives the association, and this is the line. So this is what we would expect. So what we get is it's quite close to what we would have expected. And what we expect is given by this formula. So this formula, you see sigma x bar on the left-hand side. So that's the standard deviation for sample means. That equals the sigma x, the standard deviation of individual values. Okay, so in our case 1.25 in our simulated population, divided by the square root of n, the square root of sample size. So this, what we have on the left-hand side of this formula, the standard deviation of the sample means, that's called the standard error of the mean. So the standard error of the mean equals the standard deviation of individual values divided by the square root of the sample size. And while the standard deviation of individual values gives us how much individual values on average deviate from the mean. Okay, the standard error of the mean gives us how much sample means on average deviate from the population mean. So they are the same thing, but while standard deviation, the ordinary standard deviation is for individual values, the standard error of the mean is the same thing, but for sample means instead. And you see, because we divide by the square root of n, the sample size, the higher the value on n, the larger samples we have, the smaller is the standard error of the mean. And that is exactly what we saw in our simulation. The larger samples we draw from the population, the less do the sample means tend to deviate from the population mean. The larger the sample we draw from the population, the better estimation of the population mean do we get through calculating the sample mean. Now we get back to z-scores, the formula on the left hand side here we've seen before. So the z-score, we take a value x minus the mean divided by standard deviation. So the z-score gives us how many standard deviations an observed value x deviates from the mean. Plus 1, it's 1 standard deviation above the mean, minus 2, it's 2 standard deviations below the mean, and so on. However, we can do exactly the same thing, but for sample means instead for individual values x. And that's what we get with the formula on the right-hand side here. So here we get the z-score by taking the sample mean, x bar, minus the population mean, m, divided by what we have in the denominator here is the standard error of the mean. So if we take a sample mean x bar and transform it to a z-score with this formula, we get information of how many standard errors the sample mean deviates from the population mean. Plus 1 means that the sample mean is 1 standard error above the population mean. Minus 2 means that the sample mean is located 2 standard errors below the population mean. And you see, if we have the smallest possible sample, well, it's not even called a sample, but if we have individual values, so n equals 1, then the formula on the right hand will be exactly identical with the formula on the left hand. So they are both actually the same formula. They both give us information of how much something, how much an observed value, an observed individual value, or an observed sample mean, how much it deviates from the population mean in relation to expected average deviation from the population mean. So a value of plus 1 or plus 2 or minus 2 means that the observed value, the observed individual value, or the observed sample mean deviates twice as much from the population mean than we would expect, either positively or negatively. So zeta value gives us how much an observed value deviates from the mean in relation to average expected deviation. And similarly, as we said before, z-score could be seen as a measurement of extremeness. So if you take an observed value, either an observed individual value or an observed sample mean, and transform it to a z-score, the more the z-score deviates from 0, the more extreme is the observed value or the observed sample mean. And the more extreme the value is, the more extreme the sample mean is, the lower is the probability of receiving another value, another sample mean that deviates even more from the population mean than this value does. So similarly as before, zeta value could be seen as a measurement of extremeness. The more extreme a value is, the more the zeta score will deviate from 0. As an example, imagine that Swedish women on variable depression have a population mean of 10 and a population standard deviation of 4. And on the variable IQ, Italian men have a population mean of 100 and a population standard deviation of 15. So now we ask ourselves which outcome is more probable, that 20 randomly selected Swedish women have average level and sample mean on depression that is above 12, or that 10 randomly selected Italian men have a sample mean on IQ that is less than 95. In order to answer this question, to make the comparison, we transform these values 12 and 95 to zeta scores. So if we take the value of 12 for Swedish women on depression, we take 12 minus 10, the population mean, and then we divide by the standard error of the mean, and that we get by taking the standard deviation of 4 divided by the square root of the sample size 20. And we get the zeta score of 2.24. This means that in order for this to happen, to get the sample of 20 Swedish women that has a sample mean that is above 12, we need to get the sample mean that deviates at least 2.2 standard errors from the population mean. So that's the smallest required deviation. The smallest required deviation is 2.2 standard errors. For the Italian men, for a sample of 10 individuals to have an average IQ that is less than 95, we calculate how much this is in standard errors. So we take 95 minus the population mean of 100, and we divide by the standard error of the mean. And standard error of the mean we receive by taking the standard deviation for individual values 15 divided by the size of the sample, square root of the sample size 10, and we get the value of minus 1.05. So in order for this to happen, in order for us to receive a sample of 10 Italian men with a sample mean less than 95 on the variable of IQ, we would need to get a sample with a mean that deviates at least 1.05 standard errors from the population mean. And now we see for Italian men, we would need a deviation that is at least 1.05 standard errors, while for Swedish women on depression, we would require a deviation that is at least 2.2 standard errors. And because a deviation of 2.2 standard errors is a larger deviation from the population mean, this is a more extreme outcome, and therefore this outcome is less probable. To receive a deviation that is more than 1.05 standard errors, that is a less extreme outcome, and therefore this outcome is more probable. So our answer would be that it is more probable to receive a sample of 10 Italian men with a sample mean of less than 95 on the variable IQ, compared with receiving a sample of 20 Swedish women who has a sample mean that is above 12 on the variable depression, given the sample and the population statistics. Now we're making our way into inferential statistics. And so actually this formula could be a nice one, because we could use these to calculate probabilities. So far we only used it to compare probabilities, but it might be used also to calculate actual probabilities. However, problem with this formula for the zeta score, is that it includes the standard deviation in the population, sigma as it's called here in the formula. And we seldomly know what the standard deviation in the full population is, because we don't have population data. So we don't know this. So we cannot use this. In practice, we seldomly can use this formula because it requires knowledge about the population standard deviation. So what do we do instead? Well, in this case, this is about samples. You see we have X bar in the denominator here. So it indicates that we have calculated values in a sample. So if we have a sample, if we have data from the sample, maybe we could calculate this, or not only the sample mean, but also the standard deviation within the sample. And if we calculate the standard deviation within the sample, we might use this sample standard deviation as an estimation of what the standard deviation in the population might be. And that's exactly what we do. So we replace sigma here with the population standard deviation, sigma. We replace it with the measured standard deviation in the sample. However, if we do that, there's increased uncertainty in our calculations, and we don't call this a zeta score anymore. Instead, we call it a t-value. So while this zeta formula gives us, we could say it gives us how many actual standard errors sample mean, X bar, deviates from the population mean, me. The t-value gives us how many estimated standard errors the sample mean deviates from the population mean. But otherwise, it's the same formula. So we're still making our way towards inferential statistics. And as I mentioned before, inferential statistics is about calculating probabilities. So let's start at the base here. So how do you calculate probabilities? So for instance, what is the probability for a dice to give a value that is above 4? How do you calculate that? I guess many of you know that in order to get this probability, you take the number of favorable outcomes and you divide by number of possible outcomes. So when it comes to a dice, the number of possible outcomes is 6, and the number of values that are above 4 on a dice is 2, 5, and 6. So I get this probability by taking 2, number of favorable outcomes, divided by 6, number of possible outcomes. And you receive a probability of approximately 33%. Probabilities correspond to proportions in frequency distributions. So if we throw a dice a large number of times, we will get a uniform frequency distribution. So we have equal number of 1s, 2s, 3s, and so on. So if we ask ourselves what is the probability of receiving a value that is above 4, that number of favorable outcomes correspond to the area of area A here, the green area. Number of possible outcomes correspond to the size of the full frequency distribution here. And of course, if we take the size of area A divided by the full frequency distribution, we will receive the same probability of 33%. So what this shows is that proportions in a frequency distribution correspond to probabilities. And proportions in frequency distributions correspond to probabilities, not only with uniform frequency distribution, as when we throw a dice, but for instance also normally distributed frequency distributions. So here we have a normally distributed frequency distribution. So we could ask ourselves what, with the variable v, and we could ask ourselves what is the probability of getting a value above x on this variable v. Well, that probability equals the size of area A divided by the size of the full area, the full frequency distribution, given by A plus B. So that would give the probability of receiving a value above x on this variable v. And of course, the probability of getting a value that is lower than x on this variable v correspond to the size of area B divided by the size of the full area A plus B. So again, proportions in frequency distributions correspond to probabilities. And as our goal is to calculate probabilities in inferential statistics, of course this is very useful, and also because many of the variables we are working with are at least approximately normally distributed. However, problem is that in order to use a normal frequency distribution when we calculate probabilities, is that we would need to know its location, and the location is given by the mean on the variable, and we also would need to know its peakiness, and the peakiness is given by the dispersion, for instance given by the standard deviation. So if we would like to calculate probabilities for Swedish women on the variable depression, we would need to know the mean and standard deviation on depression in the population Swedish women in order to calculate probabilities. For instance, what is the probability of receiving a value above 12? Of course, that distribution for depression among Swedish women, we cannot use that if we, for instance, wish to calculate probabilities when it comes to the variable IQ among Italian men, because that distribution doesn't have the same mean and the same standard deviation as the variable depression among Swedish women. So we would need an enormous amount of frequency distributions in order to calculate probabilities. So wouldn't it be nice if we somehow could take a variable and translate it to some other variable that always has the same mean and the same standard deviation? Because if we could do that, then we could use the same frequency distribution in order to calculate probabilities, independently of what variable we are speaking about and in what population we want to calculate the probabilities. And of course, the nice thing is that we know how to do this by now. Because by now we know that if we take a variable and zeta standardize it, so we transform each value to a zeta score with a formula we've seen before, then we receive a new variable that always has the mean 0 and a standard deviation of 1. So if we do this, then we can use the same distribution. And not surprisingly, it's called a zeta distribution in order to calculate probabilities. And this is the zeta distribution. So we see it has a mean of 0, and it has positive values above the mean and negative values below the mean. And we know, for instance, that 34% of the zeta distribution is between value 0 and value 1. And we know that value 1, a zeta score of 1, corresponds to a value that is 1 standard deviation above the mean. So this tells us if we draw an individual from a population and we have some variable that is at least approximately normally distributed, then we know that the probability of this person being somewhere between the mean and 1 standard deviation above the mean, that probability is 34%. So for instance, the probability for a Swedish woman to have a degree of depression that is somewhere between mean and 1 standard deviation above the mean, that probability is 34%. The probability for an Italian man to have an IQ that is somewhere between the mean and 1 standard deviation above the mean is also 34%. The probability for a penguin to have shoe size that is somewhere between the mean and 1 standard deviation above the mean, that probability is 34%. So if we have a normally distributed variable, the probability will always be 34% to receive a value that is somewhere between the mean and 1 standard deviation above the mean. And the probability is the same 34% to receive a value that is somewhere between the mean and 1 standard deviation below the mean, and so on. And the probability is 68% to receive a value that is somewhere between 1 standard deviation below the mean and 1 standard deviation above the mean. The probability is approximately 4% to receive a value that deviates more than 2 standard deviations from the mean, meaning that the observation will have a zeta score that is either above +2 or below -2, and so on. So this zeta distribution we can use in order to estimate probabilities independently of what population we're speaking about, independently of what variable we're speaking about, as long as the variable is at least approximately normally distributed. So let's ask ourselves the following. Imagine we draw a sample of 10 individuals from the population of Italian men, and we ask ourselves, what is the probability of these 10 Italian men to have an average IQ less than 95? So, according to this example, we know that the population mean on IQ is 100 with a standard deviation of 15. And in this case, the sample size is 10. So what do? Well, we calculate how many standard errors does this value 95 deviate from the population mean of 100. So we calculate 95 minus 100 divided by the standard error, and the standard error equals the standard deviation 15 divided by the square root of sample size 10, and we receive a value of minus 1.05. So in order for this to happen, in order to receive a sample mean that is less than 95, we will need a sample mean that is at least 1.05 standard errors below the population mean. And how high is that probability? Well, that probability corresponds to the proportion of the zeta distribution that is below, to the left of, the value minus 1.05. So let's have a look at a table with the zeta distribution. And you find these kind of tables everywhere. If you Google, you will find one. So we see here, we have 2 columns, one column with zeta scores and one column with proportion to the left. So let's find the value minus 1.05. Well, we don't have it here in the table. So let's have a look at the value minus 1.1 instead. And what does it say there? it says that 13.6% of the zeta distribution is to the left of the value minus 1.1. And we just said that this probability that we want to calculate corresponds to exactly this value. So we have our answer here. The probability for 10 randomly selected Italian men to have a sample mean less than 95, given that the population mean is 100 with a standard deviation of 15, that probability is estimated to 13.6%. Let's take another example. We ask ourselves, if we draw a sample of 20 Swedish women, what is the probability of them having an average level of depression above 12? So let's say that Swedish women on variable depression have a population mean of 10 and a population standard deviation of 4, and the sample size here is 20. So we calculate how large a deviation from the population mean would we need to have in order for this situation to be fulfilled. So we take 12 minus 10 divided by standard error. Standard error we get by taking the standard deviation of 4 and divide by the square root of the sample size 20. And we get a zeta score of 2.2. So in order for this to happen, we will need a sample with a mean that is at least 2.2 standard errors above the population mean. And what is the probability of this happening? Well, it's the same as the proportion of the zeta distribution that is above, meaning to the right of the value 2.2. So again, let's have a look at the table with the zeta values. So here we have, so let's find the value 2.2. We see it here, there it is, 2.2. What does it say? It says 0.9861. But this gives how big proportion of the zeta distribution is below, meaning to the left of this value. So 98.6% is below the value 2.2, but we want to know how big proportion is above the value 2.2. Well, if 98.6% is below, that means that 1.4% is above this value. The same probability, because the zeta distribution is symmetrical, the same proportion we see if we have a look at how big proportion of the zeta distribution is below the value minus 2.2. So if you have a look there, you see it says 1.39%, 1.4% of the zeta distribution is below minus 2.2. And the same amount is above the value plus 2.2. So the answer is the probability of 20 randomly selected Swedish women to have a sample mean on the variable depression that is about 12. That probability we estimate to 1.4%. As said before, if you calculate the zeta score, that gives how many standard errors sample mean deviates from the population mean. We need to note the standard deviation in the population. But quite commonly, I guess almost always, we don't know the standard deviation in the population. So we can't calculate the zeta score and make estimations of probabilities by looking in the zeta distribution. So how do we do then? Well, as we said before, if we don't know the standard deviation in the population, we might use the standard deviation within the sample as an estimation of this statistic. But then we don't call it a zeta score anymore. Then we call it a t-value. And as there are zeta distributions, there are also distributions of t-values, t-distributions. However, while there is only one set of distribution, there are numerous amount of t-distributions, one for each degree of freedom, as it's called. And what is degrees of freedom? Well, think like this. Imagine we have a sample of 10 individuals with a certain mean. Let's say their mean is 15 on a certain variable. So we have 10 individuals with a mean of 15. How many of those 10 values are free to vary in order for the given that the sample mean is 15? Well, 9 of those values can vary. But if 9 of those values are known and we know that the sample mean is 15, then the 10th value has to be a given value. So in a sample of 10 individuals, given that we know the sample mean, 9 values are free to vary. In a sample of 20 individuals, given that we know the sample mean, 19 of the 20 values are free to vary, and so on. So degrees of freedom, if we have one sample with one sample mean, then the degrees of freedom is number of individuals in the sample minus 1. So that's what DF stands for here, degrees of freedom. So for instance, if we have smallest possible sample with 2 individuals, then it's the uppermost distribution here. That is the t-distribution we would have a look at when estimating probabilities. So here we see that the probability for this sample to have a mean that is somewhere between the population mean and one standard error above the population mean is 25%. The probability of this sample to have a sample mean that is within one standard error from the population mean is 50%. The probability is 15% for this sample to have a mean that is more than 2 standard errors above the population mean, and so on. So if we have a small sample of 2 individuals, which gives 1 degree of freedom, then it's that t-distribution we would have take a look at when estimating probabilities. If we have a sample of 9 individuals giving 8 degrees of freedom, then it's the middlemost distribution we would look at here. Then we see, for instance, that the probability is 17% for this sample of 9 individuals to have a sample mean that is 1 standard error or more above the population mean. And the same 17% probability for this sample to have a mean that is more than 1 standard error below the population mean, and so on. 66% probability for this sample to have a mean that is within 1 standard error from the population mean. And bottom distribution here, then we have eternal amount of degrees of freedom. So we have very large sample, immensely large sample, and in this case the t-distribution is identical to the zeta distribution. So if we don't know the standard error in the population, we use the standard error, if we don't know the standard deviation in the population, we use the standard deviation in the sample as an estimation. But in that case, we calculate t-values and we use t-distributions in order to estimate probabilities. Inferential statistics is quite often used to test hypotheses. So hypotheses, they are assumptions about how things are. And we usually state different hypotheses against each other. And then with the help of the inferential statistics, we choose one of these hypotheses and claim that this hypothesis is probably the correct one. So those hypotheses, we usually have 2 of them. They're called the null hypothesis and alternative hypothesis or research hypothesis. So as an example, if we have a treatment study, so we have one group of treated individuals and a control group of non-treated patients, and we measure the level of depression after they have received, respectively not received treatment. So the null hypothesis in this case would be that treated and non-treated have the same average level of depression. So the population mean of treated equals the population mean of non-treated. The null hypothesis is not that the samples have exactly the same means, because in that case we just calculate the sample means and have a look at them. Are they the same or not? In that case, we don't need to use any inferential statistics. We don't need to calculate any probabilities. If we only want to say something about the samples, if they have the same mean, in this case, we just calculate the sample means and have a look at them. And it's very easy to decide if they are exactly the same or not. Now, inferential statistics we use when we have data from samples, but based on those data, we want to say something about the populations that the samples are representing. So even if there is a certain degree of difference between the sample means, it might still be possible for the populations to have the same mean. So the difference we observe between the sample means is due to random variation. So we calculate the probability. What is the probability for this observed difference between sample means to be due to random variation? So if we have two groups and we want to test if there is a difference between the groups' means on a certain variable, then the null hypothesis will always be that there is no difference between the population means. The two populations have the same average value on the variable in question. So if we want to test if treated and non-treated have the same level of depression, then the null hypothesis is that treated and non-treated have the same level of depression. If we want to test if there is a difference in IQ between Italian and Spanish men, then the null hypothesis is that there is no difference in average IQ between Spanish and Italian men. So the null hypothesis, if we are going to test if there's a difference between two population means, the null hypothesis is always there is no difference between the population means. Sometimes we test for correlations. We want to test, is there a correlation between X and Y in a certain population? Then the null hypothesis is that there is no correlation between X and Y in the population. So the null hypothesis is the no hypothesis. No differences between groups, no correlations between variables, no effects of anything on anything else. So that's the null hypothesis. The alternative hypothesis is then the opposite. So in this case, the treated and non-treated do not have the same average level of depression. So the population mean for treated on the variable depression is not the same as the population mean on depression for non-treated patients. So the alternative hypothesis is if we're testing if there's a difference in mean between groups, then the alternative hypothesis is that there is a difference in means between the groups. If you are testing correlations between two variables X and Y, then the alternative hypothesis claims that there is a correlation between the two variables X and Y. If we're testing if A has an effect on B, then the alternative hypothesis is that A has an effect on B, and so on. So the null and alternative hypothesis, they're the opposite of each other. And they cover all possible outcomes. So one of them has to be true. There is no third alternative. One of them has to be true. yet they have no overlap. So they can't be true, both of them at the same time. So one, but only one of them has to be true. When we conduct hypothesis testing through inferential statistics, we usually calculate something called a p-value, p standing for probability. And this p-value stands for the probability to get such a large or larger difference between sample means than we observe, given that populations have the same mean. So given that the null hypothesis is correct. So if the null hypothesis is correct, the populations have the same mean on the variable in question. What is the probability of getting two samples where the means differ this much or more from each other as we observe? And of course, sometimes we don't test if there can be assumed to be a difference between population means. Sometimes we instead test if there is a correlation between two variables x and y. So in that case, the null hypothesis is that there is no correlation between x and y in the population. So in that case, we calculate the p-value, and the p-value stands for what is the probability of getting this strong or stronger correlation between x and y in a sample of this size, given that the null hypothesis is correct, given that there is no correlation between x and y in the population in question. So generally speaking, the p-value stands for what is the probability of getting the data we have, given that the null hypothesis is correct. Or more specifically, what is the probability of getting these large or larger differences or these strong or stronger correlations, given that the null hypothesis is correct. So this is the p-value. It's a probability, estimated probability. When we do hypothesis testing with inferential statistics, we also have a significance level. It's usually called alpha value, alpha level. So the significance level is a level so this significance level is how low this p-value has to be before we are allowed to reject the null hypothesis. So in behavioral science, and usually also in medical science, this significance level is pretty much always set to 5%, so 0.05. So we say that if the calculated p-value is above 0.05, then we have to retain the null hypothesis. We are not allowed to reject it. So in this case, if we calculate the difference between two sample means and we calculate the p-value, what is the probability of getting this large or larger difference between the sample means if the population means are the same? If you calculate the p-value and it becomes larger than 5%, larger than 0.05, then we have to retain the null hypothesis. We are, so to speak, not allowed to claim that there is a difference between the population means on this variable. However, if the p-value becomes lower than the significance level, lower than 0.05, then we are allowed to reject the null hypothesis. Then we are allowed to claim that there is a difference between the means in the two populations. If we're testing a correlation between two variables x and y, and we calculate the p-value, and it becomes above 0.05, then we are not allowed to claim that there is a correlation between x and y in the population. If the p-value becomes lower than 0.05, then we are allowed to claim that there is a correlation between x and y in the population in question. So in inferential statistics, we calculate p-values, and based on this p-value, we either are allowed or not allowed to reject the null hypothesis. So when we conduct hypothesis testing with inferential statistics, we will make one of two decisions. We will either reject the null hypothesis or we'll retain it, depending on what p-value we will get from the analysis. And because the null hypothesis and the alternative hypothesis, they cover all possibilities, one of them has to be true. So the null hypothesis must be true, or it must be false, in which case the alternative hypothesis is true. So each time when we conduct hypothesis testing with inferential statistics, we will end up in one of these four boxes here. So if we reject the false null hypothesis, so for instance, we claim that there is a difference between the mean, between groups, or that there is a correlation between X and Y, or that A has an effect of B. So we reject the null hypothesis, and the null hypothesis is actually false, then we draw a correct conclusion. And that seems fine. And also, if we retain a true null hypothesis, so we say that there probably isn't any difference between the mean between groups, or that there probably isn't any correlation between X and Y, or that A has no effect on B. So we retain the null hypothesis and it's actually true. Then we also give a correct description of how things are. And of course, this might sound nice, but the downside of this is that you will not get this stuff published, not in any traditional journal anyway. So in those two cases, you give a correct description of how things are. In the other two boxes, you give a false description of how things are. So if you reject the true null hypothesis, this is called a type 1 error. So you say that there probably is, you claim that there is a difference between the group means, or that X and Y has a correlation between each other, or that A has an effect on B, but actually there is no such difference or correlation or effect. Then you conduct a type 1 error. So false positive. You find the result that is actually not true. And in the opposite direction here, you retain a false null hypothesis. So you say that there isn't any difference between group means, no correlation between X and Y, no effect of A on B. So you retain the null hypothesis, but the null hypothesis is actually false. So there is actually a difference or a correlation or an effect. So false negative. You miss something, you miss a result that actually exists. That's called a type 2 error. One important factor in research is the power of the study. And the power could be said to be the ability to find real differences or associations. Or actually, it's even simpler than that. Power is a study's probability of giving a significant result. Power is 1 minus beta, where beta stands for the risk for type 2 errors. So with no risk for type 2 errors, then we will have 100% power, and the result will always be significant. So the study will always find a difference or association. There is no risk for type 2 errors. And the power of a study increases, for instance, with the sample size. So the more individuals you have in your sample, the lower is the risk of missing a real difference or a real correlation or a real effect that exists. The lower is the risk for type 2 errors. Strength of manipulation. If a certain factor X has a causal effect on another factor Y, but you need enough of X in order to observe Y, then if you manipulate X and you do this to a high degree, then there is a higher chance of getting a significant result, then your study has higher power. For instance, if you want to study the effect of alcohol on the precision when you're throwing dart, then many of us know from experience that there might be an effect of alcohol on the precision of when you throw dart, but not at very low levels. So if you manipulate the intake of alcohol, but you only give your research group a very small amount of alcohol, then you probably won't find any effect of alcohol on the precision when throwing dart. So the strength of manipulation has an effect on the probability of finding a real effect that actually exists, and therefore it has an influence on the power of the study. Another factor is the precision of measurement, the precision of your instruments. So for instance, if we keep to the example with precision when throwing dart, of course, precision when throwing dart can be measured in several different ways. For instance, you could stand people in front of a wall, let's say 2 meters away from a wall, and you see if they hit the wall or not. So 1 for the hitting the wall and 0 for not hitting the wall. Of course, you have to be very drunk in order to not hit the wall from a distance of 2 meters. So in that case, we're measuring the precision when throwing dart with a very crude instrument, and there's a high chance of us missing a real effect of alcohol on the precision when throwing dart. So in this case, we have a very blunt instrument, and therefore our study will have low power, and there's an increased risk of us missing real differences, real effects. The risk for type 1 error in a study is usually denoted with alpha, like so many other things in statistics. This can be regulated by choosing the significance level. So for instance, if you put your significance level at 0.05, then we say that your p-value has to be lower than 0.05 before you are allowed to reject your null hypothesis. Everything else equal, if we decrease the significance level from 0.05 to 0.01, then there will be a lower risk for type 1 error. There will be a lower risk for us to receive a significant result by chance, when the null hypothesis is actually correct. So the lower the significance level, the lower is the risk for type 1 error. Of course, the downside of this is an increased risk for type 2 error. So everything else equal, with a significance level of 0.01 compared with 0.05, then we have a decreased risk for type 1 error, but also an increased risk for type 2 error. So here are a couple of examples of power as a function of sample size and the true effect. So if we have a look at the plot to the left, so this is the power here, the y-axis, is the probability of getting a significant result. And in these examples, we use a significance level of 0.05. So if the p-value is less than 0.05, then we assume that there is a difference between the population means. So the power, of course, goes from 0 to 1, from 0% to 100%. And on the x-axis, we have the sample size, and in each sample. So 10 persons in each sample, 20, 30, and so on, up to 100 persons per sample. And then we have 3 different lines for D, the true effect. So D here stands for the difference between the population means in standard deviations. So we have D, the effect size of 0.1, 0.5, 0.9. So the true difference between the population means is either 0.1, 0.5, or 0.9 standard deviations. So let's have a look. If we have a very weak effect, so the true difference between population means is only 0.1 standard deviation. That is a weak effect. Then it's the lowest line here. So we see that the power is very low. Even with quite large samples, with 100 individuals in each sample, the power is not more than 10%. So it's only 10% probability of getting a significant result, even if in this case we know there is actually a true difference between the population means, but the difference is very small. It's only 0.1 standard deviations. So in this case, due to the weak true effect, the analysis will have very low power, at least if we don't have very large samples. If we have a look at the middlemost line here, then the true difference between the population means is half a standard deviation. Here we see that the power is much higher. So for example, if we have 50 persons each in each of the samples, the power seems to be something like 0.7, so 70%. So if the true difference between the population means is 0.5 standard deviations and we have 50 persons in each sample, then the probability of getting a significant result, a p-value less than 0.05, that probability is 70%. So in 70% of the cases, we will get a significant result. In 30% of the cases, we will get a non-significant result and maybe conduct a type 2 error. And with a true difference between population means of 0.9 standard deviations, then the power quite quickly approaches 100% here. So it will never be exactly 100%, but we see here that it's almost 100% already with 50 persons in each sample. In the plot to the right, we see the same thing: power on the on the y-axis and sample size on the y-axis, x-axis. But here we analyze correlations. So in this case, raw, we have 0.1, 0.5, 0.9. That is the true correlation in the population. So what is the probability of getting a significant correlation in the sample if the true correlation in the population is 0.1, 0.5, or 0.9? Again, we see that if the true correlation in the population is weak, only 0.1, that's the lowest line, then the probability of getting a significant result, p less than 0.05, is quite small. It's very small, even with quite large sample. So in this case, the power doesn't seem to ever be above 20%. So in that case, even with a sample of 100 individuals, the probability of getting conducting type 2 error and the probability, the risk of missing this true correlation is approximately 80%. However, with a correlation of 0.5 in the population, a true correlation of 0.5, then the power is much higher. And with 0.9, it's almost 100% already with 20 persons in the sample. So what these plots show is that the power is a function both of sample size and of how strong the true effect is, how large the true difference between population means is, or how strong the true correlation in the population is. Confidence intervals is quite popular to calculate. And confidence intervals you calculate when you try to estimate what the population parameter value might be. For instance, what might the population mean be based on calculations in a sample? So as an example, here we have 10 trauma patients. I hope you see that they're trauma patients. And we measure the working memory capacity. So for these 10 individuals, we get the mean working memory capacity of 4.3, and in this sample, we get a standard deviation of 2.18. Okay, so what could the population mean be for all trauma patients on the variable working memory capacity? We think like this. Let's have a look at this table here. So this is a table of t-values. Okay, so we see here, in this case, we have a sample of 10 individuals. That means that we have 10 minus 1, 9 degrees of freedom. So if we have a look at the row here with DF9, we see that here we have some values. In the first column, we have a value of 2.262. So what does that value mean? That value means, it's the critical t-value. It means that samples of this size, of size 10, with 95% probability have a sample mean that is within 2.26 standard errors from the population mean. So if we draw a sample of 10 individuals from a certain population, we calculate the mean in the sample, then this value tells us with 95% probability, the sample mean will be somewhere between 2.26 standard errors below and 2.26 standard errors above the population mean. Okay, but what use do we have of this? Because in this case, we know the sample mean, but we try to estimate the population mean. Well, the thinking goes like this. If a sample with 95% probability is within 2.26 standard errors from the population mean, then it should be the same in the opposite direction. So with 95% probability, the population mean should be within 2.26 standard errors from the sample mean. So what we do now is that we take our sample mean to 4.3, then we add 2.26 standard errors, and standard error we get by taking the sample standard deviation 2.18 divided by the square root of the sample size 10. So we do that and we get the upper limit of our confidence interval. In this case, 5.89, 5.9. And then we do the same, but in the opposite direction. So we take our sample mean, 4.3, and we subtract the same amount of standard errors, 2.26 standard errors. So in that case, if we take 4.33 minus 2.26 standard errors, we get the value of 2.77, 2.8. So in this case, we estimate that the population mean should be somewhere between these values, 2.77 and 5.89. A traditional interpretation of this confidence interval would be that with 95% probability, the population mean is somewhere between the values 2.77 and 5.89. However, the traditional way of interpreting confidence interval is not the correct one. And well, this was actually known by the father of confidence intervals. He knew this. So in the previous example, for instance, we can actually not say that the probability is 95% that the population mean is somewhere between 2.77 and 5.89. It's a false interpretation. So the common but false interpretation is that the confidence interval gives us the probability that the probability is 95% that the population mean is a value somewhere between the lower limit and the upper limit of the confidence interval. the correct interpretation is rather that if the population mean is exactly the same as the sample mean, so in the previous example, if the population mean is exactly 4.33, then the probability is 95% that if we draw a sample of size 10 from the population, then the sample mean will be somewhere between 2.77 and 5.89. So the confidence interval is actually not an estimation of what the population mean might be. It's an estimation of what sample means will be if the population mean is exactly the same as the present sample mean. In order to demonstrate that the traditional interpretation, the false but common interpretation of the confidence interval is wrong, is false, let's have the following example. So imagine we draw a sample from a certain population, and in this sample we get a mean of 10, and we calculate the confidence interval based on the values in this sample, and we get a confidence interval that goes from 6 to 14. Okay, so in this case we would interpret, if we interpret it in the common way, that the probability is 95% that the population mean is a value somewhere between 6 and 14. Okay, but imagine the following. From the same population, we draw another sample. And in this case, the sample mean is 20. And again, we calculate the confidence interval around this sample mean, and we get a confidence interval from 16 to 24. So with a common interpretation, we would say that the probability is 95% that the population mean is a value that is somewhere between 16 and 24. So the point here is, and this could happen, of course this could happen, but the point here is that these two samples are drawn from the same population. So there is only one true population mean. So in this case, we say that the probability is 95% that the population mean is somewhere between 16 and 14. But we also say that the probability is 95% that the population mean is a value somewhere between 16 and 24. And probabilities can be added. For instance, if the probability of getting heads is 50% when you throw a dime, and the probability is 50% to get the other side, which name I can't recollect for the moment, then you can add those. So if I say it in Swedish, the probability for krona is 50% and the probability for klave is 50%. The probability for krona or klave is 50 plus 50, 100%. So you can add probabilities. So in this case, if we add those two probabilities, then we say that the probability is 95 plus 95 equals 190%, that the population mean is a value that is either between 6 and 14 or between 16 and 24. And of course, that interpretation doesn't make any sense. Of course, we cannot have a probability of 190%. Okay, so this shows that the common interpretation of what the confidence interval tells us is a false one. Rather, in this case, with the first sample, with a mean of 10, we would say that if the population mean is 10, then in 95% of the cases, if we draw samples from that population of the same size as the present sample, then the probability is 95% for the samples means to be somewhere between 6 and 14. And in the second case, we would say that the probability is 95% for sample means to be somewhere between 16 and 24. And this interpretation makes sense. It's a true interpretation. Okay. So now I will present examples of inferential statistics. So let's have a look at 3 different t-tests. We will have a look at the one sample t-test, independent samples t-test, and paired samples t-test as examples of inferential statistics. So if we start with one sample t-test, when do we use this? When we use this if we want to test if a population we are interested in might have a population mean that is a certain value. As an example, imagine we have a population here, for instance, adult Swedish women, and we wonder, might the mean in this population on the variable depression be a value of 10? So our question is, might the population mean for adult Swedish women on the variable depression be 10? So from this population, we have a sample, and in the sample, we do calculations. For instance, we get, in this example, we get a sample mean of 12. And from these calculations, we estimate, might the population mean, could the population mean be assumed to be 10? Yes or no? So we have a null hypothesis and alternative hypothesis. When we conduct the one sample t-test, we try to figure out if a certain value might be the population mean. Then the null hypothesis says that the tested value actually could be the mean on the variable in question in the population. And the alternative hypothesis says the opposite. The tested value is not the mean on the variable in question in the population. So for instance, if we want to figure out if 12 might be the population mean on depression among Swedish women, then the null hypothesis says that 12 could be the mean on depression among Swedish women, while the alternative hypothesis says that 12 is not the population mean on depression among Swedish women. So what we do is that we estimate the p-value. So for instance, if the null hypothesis says that the population mean could be 10, then we calculate, and we in our sample have a mean of 12. So what we calculate is the probability of getting a sample mean that deviates this much from, in this case, the value 10, if the null hypothesis is correct. So if the population mean actually is 10, what is the probability of getting samples of this size with a mean that deviates this much from the tested value 10? So we calculate this value. That's our p-value, the probability of getting our data if the null hypothesis is correct. And then we compare the p-value with our significance level, in our case always 0.05. So if the p-value is higher than 0.05, then we retain the null hypothesis. We say that the tested value could be the population mean. We won't claim very hard that it is. We won't say that we have proven that this is the true population mean. We just say that it could be. However, if our p-value is less than 0.05, less than the significance level, then we reject the null hypothesis in favor of the alternative hypothesis. So in this case, we would say that 10 is not the population mean on depression among Swedish women. So we reject the null hypothesis. And if we do that, then we can also say if we assume that the population mean is higher or lower than the tested value. In this case, we would say if we assume that the population mean is higher or lower than 10. And how do we calculate this p-value? Well, we do it with this formula that we have seen before. So we calculate the t-value. We calculate how many standard errors, that's the denominator in the formula, the sample mean, x bar, deviates from the tested value mu. And then we know that the larger the difference between x bar and mu, the larger the difference between the sample mean and the tested value in standard errors, the lower is the probability of the null hypothesis being correct. So if the more this t-value deviates from 0, the lower is the probability for the tested value to be the population mean. The more this t-value deviates from 0, the lower is the probability of null hypothesis being correct. So let's have an example. So let's imagine we want to figure out if Swedish women might have a population mean on the variable of depression, and that is a value of 10. So in order to answer this question, we draw a sample from the population. In this case, a sample of 25 individuals. And in this sample of 25 individuals, we calculate the sample mean on depression that equals 12. And in the sample, we get a standard deviation of 4. So what we do now is that we calculate how many standard errors this value 12 deviates from the tested value 10. So we take 12 minus 10 divided by standard error. And standard error we get by taking the sample standard deviation 4 divided by the square root of the sample size 25. So we get a t-value of 2.5. So what this tells us is that the sample mean of 12 is 2.5 standard errors above the tested value of 10. So what do we do now? Well, let's have a look in this table here. So these are critical t-values. And we go for significance level 0.05 two-tailed test. That's what we always do. So that would be the first column here. And in order to look at the right row here, we have to decide the degrees of freedom. So in this case, we have 25 individuals in one sample. That means that we have 25 minus 1, 24 degrees of freedom. So if we look at the row with 24 degrees of freedom in the first column, we see a value of 2.064. So what does that value tell us? It tells us the following. If we draw a sample from a population, a sample of size 25, then the sample mean will, with 95% probability, be somewhere between 2.06 standard errors below and 2.06 standard errors above the population mean. So this value tells us that with 95% probability, the sample mean will deviate maximally 2.06 standard errors from the population mean. So if, for instance, the population mean would be a value of 10, then the probability is 95% that a sample of this size will have a sample mean that deviates maximally 2.06 standard errors from the value 10. So we know that this will happen with 95% probability. With 95% probability, the sample mean will be somewhere within 2.06 standard errors from the value 10 if the population mean is 10. So in our case, we have just calculated that our sample mean of 12 deviates 2.5 standard errors from the value 10. So this tells us, because the value 2.5 is larger than 2.06, it tells us that the probability of this happening, if the null hypothesis is correct, if the population mean is 10, then the probability of getting a sample mean that deviates this much or more from the population, from the value 10, that probability is less than 5%. Okay, so this deviation between 12 and 10 is larger than we would expect with 95% probability if the population mean actually is 10, if the null hypothesis is correct. So what do? Well, we reject the null hypothesis. We say that our sample mean 12 deviates too much from the value 10 for us to assume that the population mean could be the value 10. So we reject the null hypothesis. We could also assume, because the sample mean 12 is higher than 10, we can assume that the population mean is a value that is larger than 10. So based on this analysis, we would conclude that the Swedish women on depression have a population mean that is a value that is above 10. Would we conduct this analysis with the statistics program, for instance SPSS, we might get an output that looks like this. Well, in this case it would look exactly like this. So here we see that we have a test value that is 10. So we test if the population mean could be a value of 10. And this doesn't show it, but the sample mean is 12. And we get t value of 2.5. So this tells us that the sample mean of 12 is 2.5 standard errors above the test value of 10. And we have 24 degrees of freedom. And then we get our p-value. That's in the box that's called sig2-tailed here. And in this case, the p-value is 0.02. So when we did it just a moment ago with the table, we came to the conclusion that the p-value is less than 0.05. And in this case, we get the more exact value, namely 0.02. So this tells us that if the population mean is 10, then the probability of getting a sample mean that deviates this much or more, 2.5 standard errors or more from the value 10, that probability is only 2%. So the probability of getting this larger or larger deviation from the value 10, if the population mean actually is 10, that probability is only 2%. And because 2% is less than 5%, we would, in this case, also, of course, similarly as we did just a moment ago, we would reject the null hypothesis. We would conclude that the population mean is not 10, but the population mean is a value that is above 10. So the next t-test is called independent samples t-test. We use this when we want to estimate if two populations can be assumed to have the same mean on a certain variable that we're interested in. So we have two populations, population 1 and 2. We don't know the population means, but we have a sample from each population. So in this case, we have sample 1 from population 1 with a sample mean of 12.9 and sample 2 from population 2 with a mean of 13.3. So clearly, we have a difference between the sample means because they are not exactly the same. 12.9 and 13.3 are not exactly the same values. However, we're not mainly interested in if there is a difference between the sample means or not. We want to use these values 12.9 and 13.3 in order to draw a conclusion whether the two populations that the samples are representing can be assumed to have the same mean on this variable. So we do this in the form of hypothesis testing and calculating inferential statistics. So we have a null hypothesis and an alternative hypothesis. And always, if we trying to figure out if two populations can be assumed to have the same mean on a certain variable, then null hypothesis is that the two populations could have the same mean on the variable in question. So, for instance, Swedish women and Norwegian women can be assumed to have the same average level of depression. So the null hypothesis states that there is no difference between the two population means. If we retain the null hypothesis, we will not claim that we have proven that the population means are exactly the same. It's only that we refrain from saying that there is a difference. That's actually what the null hypothesis. If we retain the null hypothesis, we kind of don't say anything. We are not allowed to say that there is a difference between the population means, but we have neither proven that there is not a difference between the population means, because that we retain the null hypothesis could be due to too low power in our analysis. So to retain the null hypothesis is actually not to say anything. We're not allowed to say anything. Okay, however, the alternative hypothesis says that the two populations cannot be assumed to have the same mean on the variable in question. There is a difference between the two population means. So what do we do? Well, again, we calculate the p-value. We calculate the probability of getting two sample means that deviate this much or more from each other if the null hypothesis is correct and the two populations actually have exactly the same mean on the variable in the question. So that's our p-value, that's our probability, and we have a look at this. If this p-value is larger than our significance level, larger than 0.05, then we retain the null hypothesis. We say that the two populations could have the same mean on this variable. We don't claim to have proven that they have the same mean. It's just that we cannot with enough confidence claim that there is a difference between the population means. Therefore, we have to retain the null hypothesis. If the calculated p-value is less than 0.05, less than the significance level, then we are allowed to reject the null hypothesis in favor of the alternative hypothesis. And we claim that there actually is a difference between the two population means. And if we claim that there is a difference between the two population means, then we can also say in what direction the difference goes. Which of the two populations can be assumed to have the higher and the lower mean on this variable. So how do we calculate this p-value? Well, we do it by the way of independent samples t-test, by the way of calculating a t-value. And here we see the formula for the independent samples t-test. And as you see in the denominator, we have the difference between the two sample means. So we take the mean, x bar for sample 1, minus the mean for sample 2, x bar 2. So that's the observed difference between the sample means. And in the denominator here, what we have, it's the standard error of the difference. What we get when we do the calculation of the denominator here is the expected average difference between two sample means that are drawn from populations with the same population mean. So the denominator tells us that this is how much we expect the two sample means to deviate from each other if the null hypothesis is correct. So what the t-value tells us here, how large the actual difference between the sample means are in relation to what the size of the expected size of the difference given that the null hypothesis is correct. So if the t-value is, or if the absolute t-value, because it can be both positive and negative, if the absolute t-value is less than 1, so between -1 and +1, then the difference between the two sample means is actually less than we would expect them to be if the null hypothesis is correct. And of course, in that case, we will always retain the null hypothesis. The observed difference between the sample means is actually even smaller than we would expect them to be if the null hypothesis is correct and the two populations have the same mean on this variable. If the absolute t-value is, for instance, 2, so either -2 or +2, then the difference between the two observed sample means is twice as large as we would expect the difference to be if the null hypothesis is correct. -4 +4, the difference, if the t-value is -4 or +4, then the difference between the two, the observed difference between the two sample means is 4 times as large as we would expect it to be if the null hypothesis is correct and the two populations have the same mean on the variable in question. So that's what the t-value tells us. It tells us how large the observed difference is in relation to, according to the null hypothesis, expected size of the difference. And the more the t-value deviates from 0, the lower is the probability of the null hypothesis to be correct. So here is an example of independent samples t-test. So we have a treatment study. We have given 9 patients treatment A, and we have 12 controls. And in each group, after a while, we measure the occurrence of panic attacks. And we receive, in the treatment group, we receive a sample mean of 12.9 with a standard deviation of 4.6. And in the control group, we receive a sample mean of 13.3 with a standard deviation of 5.1. So now the question is, can we, based on this data, assume that this treatment has some kind of effect on the occurrence of panic attacks? So of course, this is a new treatment, so there is actually no huge population of treated patients. These are the only 9 patients that exist. However, we could imagine that we could create such a population by giving this treatment to everybody in the patient population. So the question is not actually if there's a population difference between the existing populations of treated and non-treated patients. The question is rather, if we give this treatment to everybody in the population, would we see a change in the average level of panic attacks in the population compared with if nobody received this treatment? So the null hypothesis says that we would not observe any difference in the average level of panic attacks, while the alternative hypothesis claims that we would see a difference in the average occurrence of panic attacks. So now we'll have a look. In order to draw conclusions, we calculate how many standard errors these two sample means, 12.9 and 13.3, differ from each other. So we use the formula for independent samples t-test. And as you see, we put in the values in this formula, and we receive observed t-value of -0.19. So the difference between these two sample means, 12.9 and 13.3, is 0.19 standard errors. The reason for it that it became negative is that we used the treatment group as sample 1 and the control group as sample 2. Had we done in the opposite direction, we would have received observed t-value of plus 0.19, and the conclusion would have been exactly the same. Okay, so as I said before, if the two populations have the same mean on the variable, if the null hypothesis is correct, we expect the two sample means to differ 1 standard error of difference between, we expect them to differ one standard error of the difference from each other. So in this case, the difference between these two sample means is actually smaller than we would expect. Okay, however, let's continue. We have a look in our table with the critical t-values. So we use the significance level 0.05 with two-tailed test. So we have a look in the first column here. But which row will we have a look at? Well, that is decided by the number of degrees of freedom. So how many degrees of freedom do we have in this case? Well, we can think like this. We have two samples. In one sample, we have the mean of 12.9 and in the other 13.3. And all together, we have 9 plus 12 observed values. So we have 21 observed values. How many of these 21 values is free to vary, given that the sample means have to be 12.9 and 13.3? Well, the answer to that is that in each sample, everybody, all values except one, is free to vary. So we would have 8 degrees of freedom in the treatment group and 11 degrees of freedom in the control group, and 8 plus 11 is 19. So altogether we have 19 degrees of freedom. So let's have a look at that row. So degrees of freedom 19, and the first column, there we see a value of 2.093. So what this tells us, if we draw samples of the present sizes, so if we have two populations with the same mean, so the null hypothesis is correct, and from one of the samples we draw a sample of 9, and from the other population we draw a sample of 12, then this value tells us that with a probability of 95%, these two samples will have means that differ maximally 2.09 standard errors from each other. With 95% probability, the two sample means will be within 2.09 standard errors from each other. So, how many standard errors did our two sample means differ from each other? Well, we calculated that they differ only 0.19 standard errors from each other. And that value is much less than 2.09. So because this value 0.19 is a smaller deviation between the two sample means than a difference of 2.09 standard errors, we will retain the null hypothesis. We will say that the probability of getting this large or larger difference between the sample means, if the null hypothesis is correct, is higher than 5%, and therefore we have to retain the null hypothesis. We cannot, with enough confidence, reject the null hypothesis. We retain the null hypothesis and say that this treatment doesn't seem to have any effect on the occurrence of panic attacks. Would we conduct the analysis as we usually do with the statistical software instead? For instance, SPSS, we would get an output like this. Okay, so let's have a look at the first row here. There we see we have the t-value minus 0.189, so that's the same as we received. It's the same formula, so you receive the same value, 19 degrees of freedom, and then we get our p-value in the box sig two-tailed, and it's a value of 0.855. This value tells us that samples, if the null hypothesis is correct, the two populations have the same mean, then the probability of getting two samples with sample means that differ this much or more from each other, namely 0.19 standard errors, that probability is as high as 86%. So if the populations have the same mean, the probability of getting this larger difference between the sample means is 86%. So because that value is much higher than our significance level, 5%, we would have to retain the null hypothesis. We have not managed to show any significant difference between the two groups when it comes to the occurrence of panic attacks. Now we come to the last version of the t-test, paired samples t-test. This one we use when we have two values per individual, and we want to test if the mean on those two variables can be assumed to be the same in the population that the sample is representing. So for instance, here we see that we have two values per individual, and on one of the variables, the x variable, we have a sample mean of 4.3, and on the other variable, the y variable, we have a sample mean of 7.3. From these data, we want to estimate if the population that the sample is representing can be assumed to have the same population mean on the two variables. So the difference here is that we have one sample, but we have two values per individual. And of course, you can calculate the paired samples t-test for whatever variables you wish. You can test if people are equally tall in centimeters than they weigh in kilos, and you will hopefully, I guess, get the result that people can be assumed to be taller in centimeters than they weigh in kilos. But that doesn't sound like a very interesting analysis. So usually this analysis is used only if the two variables have been measured on the same scale. So both are measured in kilos, or both are measured in centimeters, or something like that. And traditional, classical setup is that you measure something, a variable, before and after some kind of treatment or some kind of manipulation. And in that case, you have two variables, both measured on the same scale. You have two values per individual, and you can test, is there a significant difference between the average value, the mean value, on the two occasions, before and after the manipulation. I guess it doesn't come as a surprise for you to hear that we do this in the form of hypothesis testing, inferential statistics, and that we have a null hypothesis and an alternative hypothesis. And the null hypothesis says that the means on the two variables could be the same in the population in question. So the mean, for instance, on degree of depression before and after treatment can be assumed to be the same, or they could be the same. An alternative hypothesis says the opposite. The means on the two variables are not the same in the population. For instance, the average level of depression cannot be assumed to be the same before and after the manipulation, before and after the treatment. As previously, we calculate the probability of getting the data we have, or more precisely, we calculate the probability of getting as large or larger difference between the two variables as we have in our sample if the null hypothesis is correct. And if this probability, this p-value, is larger than our significance level, larger than 0.05, we retain the null hypothesis and say that the mean on the two variables could be the same in the population that the sample is representing. If this probability, the p-value, is less than 0.05, then we reject the null hypothesis in favor of the alternative hypothesis. And in this case, we claim that the mean on the two variables cannot be assumed to be the same in the population. And if we claim that there is a difference between the mean on the two variables in the population, we can also say which of the two variables can be assumed to have the higher or the lower mean in the population. What we can do now when we have two values per person, per individual, is that for each person we can calculate the difference score, the difference between the two values. As in this example, for person 1, we take the x value 6 minus the y value 4, and the difference is 2. And we do this for all of our individuals. So for each individual, we calculate x minus y. And we see that for most of them, we have a negative value. They have a lower score on the x variable than on the y variable. But also that there is variance in this difference score. So what we can do now is that we can reformulate our null and alternative hypotheses based on this difference value. So the null hypothesis is that the average value, the mean value on the x and y variable is the same in the population that the sample is representing. However, if this is true, then the mean value on this difference variable is 0 in the population. So if the average x and the average y is the same in the population, and we have data for the full population, then we would see that the mean value on this difference variable is 0 in the population. So the null hypothesis claims that the mean difference in between x and y in the population is 0, while the alternative hypothesis claims the opposite, that the mean difference for the difference between x and y is not 0 in the population. And now when we have calculated such a difference score for each individual, what we actually will do is one sample t-test, where the tested value is 0 and the variable we are testing is the difference variable. So we have this formula, we calculate the t-value, but this formula is exactly the same as the formula for the one sample t-test. It's just that we, instead of x, we used the letter D here in order to emphasize that we are working with a difference variable. So we take the mean difference in the sample divided by the standard error on the difference variable. And the standard error we receive by taking the standard deviation on the difference variable divided by the square root of the sample size. If we would like to emphasize this, that this is exactly the same formula as the one sample t-test, we could also in the denominator add -0. But it's been omitted here because usually, or almost always, when you conduct a paired samples t-test, the tested value is 0. Okay, so we calculate the t-value with this formula, and so we will receive, the t-value will tell us how many standard errors the mean difference in the sample differs from 0. And the more the mean difference in the sample differs from 0, the lower is the probability for the null hypothesis to be correct. And the more the mean difference in the sample differs from 0, the more the calculated t-value will differ also from 0. So, as an example of paired samples t-test, imagine that we have six trauma patients. We measure the working memory capacity directly after the trauma and after 2 years. So T1, time 1, directly after the trauma, and T2 after 2 years. So at T1, we get values 6, 7, 3, and so on. And at T2, for the same 6 patients, we get values 4, 9, 7, and so on. So what we can do now is that we calculate the difference score for each person, and we take T1 minus T2. So that might be a bit counterintuitive. Usually you might want to calculate T2 minus T1, so a positive value stands for an increase and a negative value for a decrease, but in this case it's the opposite. This won't, of course, affect your interpretation in the end. You get exactly the same results independently, irrespective of in what direction you calculate your difference score. But this is how it's quite often done in statistical software, so I followed that example. So we see patient 1 has a difference of 2, so a score that is this person has a better working memory capacity at T1 compared with T2. Patient 2 has a difference of -2, and so on. So all but patient 1 have increased their working memory capacity after 2 years compared with directly after the trauma, but to different degrees. If we calculate the mean value on this difference variable, we get a value of -3. So this means that we have an average increase in the working memory capacity by 3 points. And the standard deviation on this difference variable is 2.8. So we calculate the t-value by taking this average difference in the sample, -3, divided by the standard error. And the standard error we receive by taking the standard deviation, 2.8, divided by the square root of the sample size 6. And we receive a value of -2.6. This value tells us that this average difference, -3, is 2.6 standard errors below value 0. Okay, now we could compare this value, -2.6, with expected value in a table with t-scores. So here we have our table with t-scores. So we have a look in the first column, because we're always using significance level 0.05 with two-tail testing. So we keep to column 1, but which row should we look at? Well, here we have one sample, and we have 6 values, because we have 6 difference values, one from each patient. And the mean on that difference variable is -3. So how many of these 6 values are free to vary, given that the average difference have to be -3? Well, that's 6 minus 1. So 5 of these values are free to vary. So we have a look in the first column for 5 degrees of freedom, and there we see a value of 2.571. So this tells us that samples of this size with 95% probability have a sample mean that is within 2.57 standard errors from the population mean. So if the population mean, for instance, would be a value of 0, we expect with 95% probability that samples drawn from that population will have a sample mean that is within 2.57 standard errors from 0. So how much did our sample mean differ from 0? How much did our sample mean of -3 differ from 0? Well, we just calculated that it differs 2.6 standard errors from 0. So the difference between -3 and 0 in standard errors is larger than we would expect if the population mean is 0. The probability of getting sample mean that differs this much from zero if the population mean is zero is less than 5%. Because we know that with 95% probability, the sample mean would be within 2.57 standard errors from zero. Okay, so what conclusion do we draw? Well, because 2.6 minus 2.6 is outside the range from minus 2.57 to plus 2.57, we are allowed to reject the null hypothesis. So we reject the null hypothesis. We claim that the memory capacity is not the same directly after 2 years. And we can also, because we claim that there is a difference, we can say in what direction it goes. And based on the data we see here, we see that on average, the 6 patients have increased in memory capacity from directly after to 2 years after the trauma. So based on these data, we would claim that on average, trauma patients will have a higher memory capacity 2 years after compared with directly after the trauma. Had we conducted this with statistical software, for instance SPSS, we would get an output like this. So this is based on exactly the same data. So we see mean difference score in this sample of -3 and a standard deviation on the difference variable 2.8 and a standard error on the difference variable of 1.15. And that standard error of the difference we would receive if we take our standard deviation 2.8 and divide it by the square root of the sample size, square root of 6. So it's exactly the same thing as we have in our denominator in our formula. Okay, if we now take -3, the mean difference in our sample, and divide it by its standard error 1.15, we receive the t-value -2.59, -2.6. So it's exactly the same value as we received because it's the same data, it's the same formula. Okay, and we have 5 degrees of freedom, and then we get our p-value sig2-tailed 0.048. So this value tells us that if the population mean is 0, then the probability of getting a sample mean for samples of this size that differs this much or more from 0, 2.6 or more standard errors from 0, that probability is 4.8%. And because 4.8% is less than 5%, we would reject the null hypothesis. We would claim that trauma patients cannot be assumed to have the same memory capacity after 2 years compared with directly after the trauma on average. We would claim that trauma patients on average have a better memory capacity 2 years after the trauma compared with directly after the trauma. So that was our paired samples t-test. That was actually all for this introduction lecture. So I thank you all. You've been excellent listeners. Thank you, and we might see later. Goodbye.